Hi, welcome back. In this video, we're going to look at a couple of different ways to represent a system of linear equations using matrices. So we're going to represent this system, x1 minus x2 plus 3x3 equals 9, negative x1 plus 3x2 minus x3 equals negative 6, 2x1 minus 5x2 plus 5x3 equals 17. We're going to represent this in two different matrix equations. So the first matrix equation is just the coefficient matrix of the system multiplied by what we call a column vector whose components are just the three unknowns, x1, x2, and x3. And we're going to set this equal to another matrix. Well, the other matrix, because we're multiplying a 3 by 3 times a 3 by 1, the resulting matrix is going to be a 3 by 1 as well. So that's called a column vector. And it turns out that the components are 9, negative 6, 17, the numbers on the right side of the system. And you can check that by doing the multiplication on the left side of this equation. If you go across the first row of the coefficient matrix and down the column vector, you get x1 minus 2x2 plus 3x3 equals 9. You get the first equation in the linear system. So this matrix equation represents that system. Another matrix equation we could write down for that system is x1, the first unknown, multiplied by the first column of the coefficient matrix, plus x2 multiplied by the second column of the coefficient matrix, plus x3 times the third column. That's also equal to the column vector consisting of the numbers on the right side of the system. And if you do the math on the left side, if you multiply the first column vector by x1 and add it to x2 times the second column vector and add that to x3 times the third column vector, you will get the matrix product right above, and you'll get the system that they both represent. So as I mentioned, this is on the left side of this equation. This is called a linear combination of column vectors. So column vectors are just the columns of some matrix written as n by 1 matrix. And a linear combination means a sum of scalar multiples of something. So that's what we have on the left side of the second equation. Now the first equation is also represented as a times x is equal to b. And notice my notation. I wrote x with a little arrow on top, and I wrote b with an arrow on top. The arrow on top means I'm talking about a vector. So the vector x is the column vector x1, x2, x3. And the vector b is the column vector 9, negative 6, 17. All right, so let's talk about that notation for a moment. So you're reading the textbook and you're taking notes. You're also watching videos and taking notes, and coming to class and taking notes. In the textbook, they can use boldface letters that we can't use when we write in our notes or when I write when I'm giving a lecture or making a video. So notice here, the capital A, we know what that stands for. It's not boldface, it's a regular old capital letter A that we know that always means a matrix. But the boldface X next to it is the textbook notation for a column vector. Because they can do boldface in a textbook, they don't have to put little arrows on top. But when you write it in your notes, you need to put an arrow on top because you can't do boldface in your notes. So it's really important that you use the correct notation. And notice the A1, A2, AN, those are also boldface. Well, those are the columns of a coefficient matrix. So those are column vectors. And in your notes, you got to put little arrows on top. So anything that's boldface in the book has arrows on, or I call them hats. They're wearing little hats because they're vectors. In your notes, the vector B, it's boldface in the book, but in your notes, it has to have a little hat on it or an arrow. So what are these other variables that are not boldface? So anything that does not have boldface, if it's not a capital letter, so this is a lowercase x with a subscript 1, a lowercase x2, lowercase xn, A11, A12, A1n, these are all lowercase and they're not boldface. So those are scalars. Those are always going to represent real numbers, just like in a calculus class, right? An x, lowercase x, that's italics. It's not boldface in your calculus class. That was a real number. So same thing here. So they don't have arrows. So you just write them the same way that the textbook writes them. It's really important that you use the correct notation in your notes, and in anything that you turn into me needs to have the correct notation. If you type something up, for example, in your written assignment, you need to use either boldface for the vectors or an arrow on it, or a hat for vectors, okay? Anything without an arrow or without a hat that is not boldface is a scalar. So you've got to get into the habit of using the correct notation. All right, let's look at an example. Here we've got a matrix A, a 3x3 matrix, and a column vector B, 1, 3, 2. And it says write B as a linear combination of the columns of A. So I'm just going to give the columns names. I'm going to call them vectors A1, A2, and A3. Notice I had to put hats on my A's because I can't do boldface. Those are vectors. And also B is a vector, so I'm writing it with an arrow or a hat. All right, so what does the linear combination mean? That means that there are numbers, C1, C2, C3, such that C1 times the first column plus C2 times the second column plus C3 times the third is going to be equal to the vector B. And so we need to find, in order to write B as a linear combination, we need to find those numbers, C1, C2, C3, that make this equation true. So if I go ahead and multiply the first vector by C1, I get C1, negative C1, 0. And then the second vector becomes 2C2, 0, C2. The third vector is 4C3, 2C3, 3C3, and that's all equal to B. And now, if I go across, I see that when I add the corresponding components on the left side, I get C1 plus 2C2 plus 4C3, and that has to be equal to 1. So I get this equation, C1 plus 2C2 plus 4C3 equals 1. The second entry is negative C1 plus 2C3 equals 3. And the third equation is C2 plus 3C3 equals 2. Now, this is a system, and I can write the augmented matrix for that system. And I can do a little Gauss-Jordan magic on that augmented matrix. And I get the reduced row echelon form of the augmented matrix. I get 1, 0, negative 2, negative 3, 0, 1, 3, 2, and a row of zeros, which means the first equation is C1 minus 2C3 equals negative 3. The second equation is C2 plus 3C3 equals 2, and then there is no third equation. So these two equations, I can solve each one for one of the unknowns. So the first one I solve for C1, and C1 is negative 3 plus 2C3. And I solve the second one for C2. I get C2 is 2 minus 3C3. Now this means that I have a free variable. I can introduce a parameter. But I just need one solution to this system. Okay, I don't need all of them. I have infinitely many, but I just need one. Because C3 can be anything I want, the simplest one to choose is let C3 be 0. If C3 is 0, then C1 is -3 and C2 is +2. And I can write my linear combination. I can write B as -3 times A1, the first column vector, plus 2 times A2, the second column vector. And that's my linear combination. So we'll see a lot of linear combinations of vectors, and we'll be using matrix equations a lot for the rest of this semester. And I'll see you in some other video.